Hello, Colin. All right.
Hey,
Hello. Hey, all right. And hey, Brendan. Hello. Good morning. Good morning. Good morning. And hello, Xavier. This is like you guys are a steady crew, I have to say. You're a very reliable crew. And Brittany, same deal. Good morning. Good morning.
morning.
Good morning. Good morning, all. Who else am I? Okay, wait, sorry. Um, of course, being told you're reliable by me is like a mixed. I mean, like I'm not sure I'm the metric, but Emily, good morning. Judith, good morning. Alexis, good morning. Charlene, good morning. Now the chat, and I will admit also, yeah, I don't need anything. I just want stuff. All right, wait, chat. We will start in a second. Just getting my life together. Good morning, Ariana. Good morning, Gaia. Guy cleverly left out the adjective just to leave things open in case it's like a horrible morning. Fair enough. Good morning, Judith. Same thing with Charlene. Wait, it's like, did Charlene and Gaia go shopping this together this morning? They both totally, I don't mean shopping, but I mean whatever. Good morning. Good morning. Good morning, Michaela. Good morning, Anissa. Good morning, Alexis. See, they left off the adjectives, but she gave a double exclamation point. So it's like all balanced out. And I'm just being weird. There's a surprise. Good morning, Ananelsi. Good morning, direct chat. Wait, sorry, more people in the. Good morning, Carolina. Nah, not yet. All right, I assume the shopping has not happened yet. All right. Um, um, Good morning, Maria. Okay. Oh, and Stephanie. Good morning. All right. I think that. Oh, and there's more. Okay. Hold on. Okay. Um. Okay. All right. So let's get girl. Oh wait. Who else did I? Oh, and good morning, Nat. Kaya. All right. I see. Well, I'm glad that everybody. I'm glad. Okay. Sorry. There's obviously things going on in the direct chat, which are just like whatever. Okay. Which just shows that whatever disease I have, whatever psychological disease I have is apparently contagious. So let's be careful. Good morning, Nasreen. Okay, let's do physics. Again, hopefully during your break, hopefully I will catch up with you. Um, I say hopefully, because taking credit for, okay, I'm gonna stop looking at the chat because oh, butterfly. Okay. Right. I will hopefully catch up with you during the break, hopefully. But it will all come out in the wash. Right now, we'll just proceed on with, but I am aware that you have been doing tons of work, that is in my box now. And that is credit to you. And I'm just going to keep rolling. I'm just acknowledging. And the longer I take with certain things, the, the more I understand that I've taken too long and the more the benefit goes to you. I can assure you of that. You do not get punished for my negligence or my time management. Those who cannot do, teach, and those who cannot manage space and time teach physics. Okay, just kidding. So the board, all right. So let's go back to physics. That long way of saying we're just going to keep pressing on with the material here. Um, and by the material, I mean continuing where we were Monday. Um, with I'm going over homework. I'm still just even though now you've just handed in, and I think many of you, as which is good. I'm still just proceeding through like aspects of homework number 8. Um, But the big picture, whether you care about the homework or not, the big picture here is how do we draw force diagrams so that we know what to plug in to the left side of F net equals MA in order to then predict the A of some M. Like really, like that's the picture. I mean, that's the topic. So I'm gonna do the screen share thing again in a second and just go back and show you what problem we're talking about. But in terms of the summary, again, like the law is F net equals MA. Newton's second law is F net equals MA. The sum of all of the forces acting on some M on some mass produces the acceleration of that mass, right? Like that's the law. And then what I'm trying to emphasize is that's a vector equation, right? That's a vector equation. So what that really means is simultaneously yet independently, all the forces acting on the x-axis will produce the x component of acceleration. All the forces acting on the y-axis will produce the y component of acceleration, etc. Right? And when I say all the forces on each axis, I then mean to include minus signs. So any force, right? So it's the sum of all the forces acting on each axis produces the acceleration on that axis. And when we say the sum, we mean add up all the forces, but we mean all the forces going in one direction on a axis get a positive sign, and all the forces going in the opposite direction get a negative sign, right? So it's still addition, but we're accounting for direction. And you notice, quick sidebar, you notice how like we spent all this time on the first homework on the number line, on just someone like going back and forth, one dimension of space, which like seems like very primitive at the time that we're doing it, maybe. But the reason is because no matter how advanced and complex physics increasingly gets, we're always like reducing all the situations back to that. That's right. So to a series of axes and simple pluses and minuses that are going on each axis. Okay. So now the issue is how do, like, if we have a whole bunch of things happening to some object, how do we reduce everything that's happening to just a series of one-dimensional assessments for which in each one dimension there's some set of pushes and pulls that we're just going to add up, right? Like, because that's what we're going to do. So the idea is we begin with a system schema. That's what we were saying Monday, right? And what you were saying in the lab, I think last week. We start with a system schema that allows us to unambiguously identify all of the forces acting on the mass, right? And the point of the system schema is to force us, I mean, really, is to make it so that we don't have to think, or certainly that we don't have to think incorrectly. Like the system schema is saying, if you want to know whether there's a force acting on an object, then you better just look at all the other objects in the world that are pushing or pulling on that object. Like the real lesson of the system schema is do not say that there is a force acting on something unless you can identify something else that is the source of that force. Like a force is an interaction between two actual objects. Okay, so the system schema first says you want to know what's happening to your mass, no matter how complicated it might look. You got to ask yourself what else in the world is pushing or pulling on it. And the way to answer that question, we said, was first of all, recognize planet Earth because it's just always there. It's always there. And it's got this weird property of being able to push or pull without touching. So put that in there first. And then it says, then look at everything else and only anything else that's touching your object. It's literally that concrete, right? So the system schema does that. Then, and the system schema provides us with a bunch of lines, literal, like line segments. And if we do it correctly and we follow some of the intricacies of the rule that I mentioned, of the rules that I mentioned Monday, like there's some intricacies, like certain kind of touches actually produce two lines, right? But once you follow the intricacies of the rules, then you have a bunch of lines in your system schema, and then you say, aha, okay, the lines came from circles. The circles were objects that I could name in the world. Now the lines are the forces. So now I move my attention to a free body diagram, a pure free body diagram, which converts each and only each one of those line segments into an arrow. Each arrow is now a force. It's now now that I know that it's there, I can get more specific about it. So I make it into a force arrow, with a tip and a tail. And so now I'm going to focus on what direction it's actually pushing or pulling in, right? So I'm getting more detailed. I'm turning it into a vector now so I can start doing math almost and plugging into these equations. But then once I draw it as an arrow with a specific direction and perhaps even a comparative magnitude, then I probably end up giving the arrow some kind of name or some kind of mathematical symbol, because now I'm viewing that arrow as a force unto itself. Like again, I cannot emphasize enough. Originally, you don't acknowledge a force unless you can acknowledge that there's two objects interacting. Once you can name those two objects and you say, yeah, okay, there's definitely a force here, now you're confident. So now you forget about the other object that was making the force and you just focus on the force itself, right? Right. And now then it gets some kind of name or some kind of mathematical symbol that will allow it ultimately to be plugged into the left side of F net equals MA, right? So we're going on a process here to ultimately set up the math. And ultimately do the math. And we're just about now where, so now I'm going to go back to all this. Like this has been almost where we picked up. Yes, where we left off Monday. But just to complete the summary for whatever reason, once the arrows have names or mathematical symbols in this pure free body diagram, just to know, then there's often, once the situation gets complicated enough, or once if there's any angles or anything involved, then often each one of these vector arrows then will have to be broken up into an X part and a Y part or a Z part. Right now they're vectors. Now we're going to relate their X. We're going to treat them just like velocity vectors or displacement vectors. We're going to add up their constituent X components and or Y components and or Z components. And therefore, sometimes what this then means is we're going to have to break up the vectors into X and Y components and make yet a third diagram, a third and final diagram called the component free body diagram. Once we have a diagram that just has arrows pointing along each individual assigned axis, like once we have a diagram for which we have only arrows in it, and every arrow appears on an axis, like it has the same direction as a coordinate axis, then we take the values of those arrows and plug them into the left side of F net equals MA, and we do the math and we predict the acceleration of the object, or like whatever the case may be. That's the procedure. Okay, that's the procedure. I'm about to go back and continue doing it on some of these homework problems from homework 8. But I also, before I turn the page, do the screen share, whatever, I also just, I guess, want to throw in this little plug. Like, this is like part of the reason that we so strictly try to emphasize and practice the 5-step method before we even get to this stage. Because the one thing I want you to have gotten used to, like now that we're here at sort of like kind of like the heart of classical mechanics, the heart of classical mechanics is like applying Newton's laws. I want you to see that the thing that's sort of one of the kind of secret techniques of physics, or the things that make physics a lot easier once you get used to it, but makes it counterintuitive and sort of unexpected at first when you're not used to it, is that physics is like all about setup. right? Like just note that even I just talked for 10 minutes. I'm sure, I'm sure it's time that I move on. But notice that like here's the equation sitting on the board, right? And it's very easy to think that physics is all about equations and plugging into equations and doing the math that is necessary for the equations. But what we're sort of trying to emphasize here is that by the time you're computing the mathematics of an equation in physics, by the time you're doing that, you're kind of already in the comfortable off and running part. Like that's the part that sort of takes care of itself. I mean, not literally, but that's the part where the machine progresses forward according to laws of mathematics that actually almost all of you are far better at than some of you think. Like the computation part is the comfortable part. And many of us notice this as we're going through physics. We're like, oh, I can do it. I just can't start it. Or I can do it, but I just don't know. I'm like, once he shows me, but I never know how to do it on my own. Well, because the part of the secret is that what physics really is the art of knowing how to set up the situation so that the correct math will then get done. So in Newton's law is right. So that it's really all about doing steps 1, 2, and 3 properly so that then step 4 does take care of itself. And in the case of Newton's laws, the good news is you've now practiced that way of thinking in honestly in conditions that are in a way harder and more boring in a way with all the kinematic stuff that you've been doing. With Newton's laws, steps 1, 2, and 3, so to speak, are actually themselves procedures if you just learn to follow them. You actually don't have to be as creative. Steps 1, 2, and 3 are, in effect, set up system schema, pure free body diagram, component free body diagram. If you really take the diagram seriously, if you follow the rules and you don't just think of them as rough sketches, but you think of them as computational tools that will set up the numerical computation, then they will do the work for you. I mean, okay, that's the picture of the pictures. Okay, that's why we spend so much time on them. So, okay, I'm sorry to interrupt. I mean, so I'm going to switch screen. There's something in the chat. I'm going to switch screens, tell you where I'm at with, and go back to the homework problems. But wait, okay. Oh, sorry. Oh, wait, okay. Wait, no, thank you. I do this every time. No, I'm glad there's something in the break that I'm something in the break, something in the chat that is totally helpful to the class because once again I've done a scheduling error with the homework. So wait, let me just read this and fix homework. Oh no, yeah, thank you. No, okay. One of your classmates, you should probably, I don't want to give anybody away, but you totally want to thank one of your classmates, hopefully, because he or she um it just pointed out that I'd accidentally assigned this homework or a homework. I guess not this one. I accidentally assigned a homework for the middle of break. That is not what I meant to do. I think I totally did not know when break was when I did this. I will fix it right now. I don't want you to have anything. What I want you to do during break, of course, my fantasy is that you would think about physics at some level. But if you're going to think about physics during break, you either want it to be that you're just getting together and talking about physics accidentally inform, or you're like catching up and recalibrating as I will attempt to do. No, I don't want you doing new homework during break. Hold on, I will change that right now. I'm just looking. Bear with me for a second. But yes, thank you, person who just pointed that out. That is not on purpose. And I know, and if homework 8 was due today, well, I'll look at that in this. We'll actually see. Impressive. I know this because we're getting to that point in the semester where you see that I'm behind and where everybody's tired and burnt out and needs a break. And I'll admit, 9 out of 21 of you have already handed in the homework 8 that's due today. Honestly, I'm not going to mention names right now. I don't think, but I see that you did. I might mention names in a second, but if you already handed in homework 9, that means you're really still very on top of things, and that's impressive. If you did not turn in yet homework 8, it's understandable. Again, like obviously I'm starting to fall apart at this point of the semester too. Just to be clear, again, you certainly still can and should because it will be very helpful for the final and for next semester and stuff. I mean, and even if you can't get literally all the points, it'll still be well worth your while to turn in homework 8. So use the break to catch up on things like that. Also, okay, I'm fixing this right now. Hold on, I'm trying to do things at once, which I totally cannot because I can't even do one thing at once. Hold on. So no, I'm changing that. I think I can even make it through the middle of the next week. Wait, let me just see. I don't even want you to have to do. Bear with me for a second. If I do that, then there's one. All right, I think I'm shuffling them all. I'm adjusting them all so it it's it I don't the ideas get more intense, increasingly intense as we go. I don't mean for your life to get more stressful as we go. Hold on. So that's April 30th. Last day of classes is like May. Hold on. All right, hold on. All right. I think it's all okay now. In other words, I thank you to the person. I just changed homework 9 to be due the 23rd, which means it's not even due the Monday you get back because I don't really want you to work during break. It's due the Wednesday. I mean, it's still a long homework, blah, 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 blah. So, all right, I adjusted that. Oh my God. And someone, while I was talking, someone just turned in. Well, that was clever. Someone just turned in homework 8. Okay. So, yeah, okay. I think it's all. There was one other little thing I was just going to say about homework. Oh, wait. Sorry, I'm gonna go back to but that just made me realize something about the homeworks. Homework 7. Oh well. Oh, yes, yes. Also, pro tip, just in terms of managing this class or Physics 204, especially if hopefully I get the pleasure of seeing you in that class. Um, the pro tip is if you're ever having an impulse to try to catch up, whatever that means, right? If you're trying to catch up and like fill past gaps, either stuff you just never did or improvements of stuff that you did do. The main pro tip is go backwards. If you're going to try to catch up, this may sound weird, and that's why I'm saying it. Don't start, like, go to the most recent thing first and see what you can do and try to do that, whatever it is, the most recent thing. Then, if you are struggling with it, or if it's like, I don't even understand what this is because I didn't understand okay, fine. Then use that as a motivation and a recognition to take another step backwards. But don't you know what I'm saying? Go backwards when you try to catch up. Same thing with studying. Like, look at the most recent stuff and then see how far back you have to go from that. I'll just leave it at that. I think that's a wise thing to do in physics, a realistic thing. Okay. Okay. Got you. Okay. I'll put a note to that. A direct chat person about who just turned in the homework. I'm going to put a note in so I know, so I don't like later think it was late. Hold on, because I do trust you because I know who you are. Oh wait, it doesn't even say that. Sorry. We will get back to the program in a second, but I'm glad we're whatever tying up loose ends right now. Yeah, okay, hold on. Okay. Um, and then the other pro tip about that, I think I've mentioned this, but just if we're getting to that point in the semester where on the one hand people are tired, on the other hand people are trying to catch up, on the other hand people might be starting to get twitchy about their grades or whatever. The other thing is if during break, if you're looking back at old stuff and just seeing where can I get more points or where can I, close gaps. I may have mentioned this, but I just want to reinforce again. I'm going to try to catch up as well, right? But I'm going to have to triage just like you. And of course, my first priority, the main thing is your exams. So if you ever see an old homework assignment where you did turn it in and you did get a bunch of points, but you didn't get all the points, and you're looking and thinking, I wonder if I can get more of the points. If you find such an old homework assignment, it may be the case that I never gave you feedback on it. If that is the case, since I'm scrambling to catch up too, if you see an old homework where you got a bunch of points, but not, especially if you know that you turned it in on time, or if it doesn't say done late, right? Look at it And it's a very good exercise to help you and help me, like for the final and everything. Look at it. If you're like, oh, I see what I needed to, like I never turned in like the third problem, or oh yeah, now that we've learned this stuff, I see that this was all wrong, or like whatever. If you see on your own a way to improve the submission and get more points, just feel free to do that. Honestly, like save us both the step and just upload a revision and leave the old one there, but just upload a revision and say catching up, wanting more points or whatever. And I will definitely notice that. I'll definitely look at that. I'll also be appreciative that you might have saved us both the need to do intermediary feedback and you'll get more points. Or if you look at the thing and you're like, no, like I didn't get all the points for whatever reason, but I honestly don't even see the reason. I feel like it's all here. I feel like I did everything. I'm still waiting for him to tell me what's wrong. Okay, that or I don't even believe that anything is wrong. Then just write me a quick note, like literally say, I've reviewed this assignment and I still need feedback to get the more points, or I still don't know what's wrong. And then that will accelerate my process. And or I might look at it and be like, oh no, she's right, or he's right. Like, oh, I totally just owe her all the points, or him. And then I'll just do that. All right. It's just a way for us both to triage. Okay. I hope that's clear. Um, okay, I hope that's clear. Okay. They saved a nation. Okay. They saved a nation. Right. All right. Sorry for that whole interruption, but hopefully that does help us all optimize our situation in the class and optimize break. Um, okay. Therefore, I'm going to now switch. I'm going to go back to the problem we were doing before and the notes that we were doing before. All right, quick screen share. We are wait, no, not quick. Sorry, sir. We are okay. Quick screen share. Okay, we were here on this problem number 3, multi-force warm-ups. We were talking about the apple. We're in the middle. Oh, yeah, and we're almost done with it. We were on part 3 of problem 3. We drew an FBD of the apple. That's what I'm going to go back to in a minute. The last thing we had said about that FBD that I want to emphasize, like, well, or I'll just go back. Okay, we were at drawing the FBD of the apple. There's 2 arrows in the FBD, the pure free body diagram. There's 2 arrows explicitly because there were 2 line segments in the system schema. Like that's the whole idea, is that every line segment from the system schema gets lifted over and becomes a vector arrow in the pure free body diagram. And then you're going to trust that to make your next. So had just made an FBD of the apple. So it has 2 arrows in it, one going up and one going down. Uh, So let me okay. So tell me if you don't know, but that's where I am. And I'm going to continue with that. Problem 3 here on the board, part 3, draw an FBD of the apple that's sitting on a table. Okay. Okay. This is the pure FBD of the apple on the table, right? This is where we left off. Couple of comments. Surprise, surprise. One, is that down arrow, mg. I want that to be clear in your minds. Like, yes, ultimately it sort of becomes a memorizer, but be sure you're comfortable with it. The down arrow that you see that's labeled mg is in every single free body diagram ever in classical mechanics. Like, it's like the first arrow you draw in every single diagram, no matter how complicated, because it's basically saying the earth is always there pulling down on your mass, whatever mass you're focusing on. And it's saying that the pull of the earth on your mass, the pull is mass times g. Uh, right? The mass is m. The acceleration due to any object when only gravity is acting on it is g. So the force of gravity is m times g. Okay, and the English word for that is weight, but the mathematical truth of it is m times g every single time. So the weight of any object in newtons, the weight, the gravitational force pulling down on any and every object at the surface of the earth is a number of newtons that equals the object's mass in kilograms times 9.8 meters per second squared. Okay, so that's the weight. That's there every time. Then there's this, in this diagram, there's this upward force from the table, right? Like there's an object called a table that is underneath the apple. And that table is touching the apple from underneath. It's underneath the apple and it's touching it. So, and if the table weren't there, the apple would fall down. So the table is pushing the apple up, right? That's what we're saying. Now, we already established that it was a table in the other diagram. And we established in the other diagram that a table is touching the apple. So that's what convinces us that there's a force coming from that table acting on the apple. So now we've put that upward force in this diagram, and we no longer care that it's the table anymore, right? We now just care that there's an upward force on the apple, and we give it a name now because we're just focused on the force itself. We give it a name. The name is normal force. And the normal force, I mean, this is, and I know that a lot of you saw this in high school. I'm not thinking that I'm the first person that's ever told you this word, but I am saying that there's a lot of misconceptions and misunderstandings that surround this word or this arrow. So let me be as clear as I can. The normal force, um, okay. So the normal force, means perpendicular. Normal means perpendicular. It does not mean anything else. It doesn't mean like typical or customary or average. Like okay, it doesn't mean it means perpendicular. So whenever, remember, I made a big weird stink about like surfaces pressing on each other, like when I was talking about the system schemas. Well, yeah, whenever and only whenever there are two surfaces pressing against each other, pushing against each other, pushing as opposed to pulling. When surfaces are pushing against each other, the push of one surface against the other that is directed perpendicular to the plane of contact, right? So when my hands press against each other, you can imagine this Euclidean, like in plane, like sandwiched between my two hands, like wherever my hands are going, there's that plane in between them. So imagine a line, an axis that's perpendicular to that plane. Whatever's happening along that line is what we call, well, we call the normal line, but we call that force the normal force. You can see I'm serious about this because this gets, it's like really simple and straightforward and reliable, like once you get it. But like this is a kind of thing that throws people off in physics. So when I say, if I say right now, sorry, hold on one second. Okay. If right, you see this the coaster on my hand. When I say that my hand is exerting a normal force on that coaster, I just mean that my hand is pressing up against the coaster. If my hand were at an angle, it'd be pressing against the coaster at an angle. I would say the normal force is acting at an angle. The normal force is just the pressing from my hand again from one surface against another surface in that direction, like perpendicular to the plane between the two surfaces. Okay. It's always there when two surfaces are pushing against each other. And by the way, whether the surfaces are smooth or not, it's there. But the thing I want to emphasize before I move on is it's only there when two surfaces are pressing against each other. Part of the problem with the word normal is it makes people feel like it's like normally there. Like not all diagrams have mg in them. Not all diagrams have n in them. And just because you see mg does not mean you should automatically put in an n. That is a thing that people a lot of times accidentally do in high school. I mean, no, with all respect, I mean, but that when people are, anyway, don't think that normal automatically is there just because gravity is there. And don't think that normal is like automatically related to gravity in any particular, it isn't. Now here, in this simple case, it does happen to be. There's weight pulling down on the object and there's normal pulling up. Excuse me, pushing up, normal from the desk, weight from the earth. That's what's happening in our pure free body diagram. Okay. And it's because we followed the rules of the system schema. I'm just looking at the chat. Okay. One other thing I'm going to say, I'm about to go to the next question 4, I'm pretty sure. But that's my pure free body diagram. Okay. And what I would do next, I mean, whether the question, what if this were like if I were solving an abstract problem or this were the lab or something, the next thing I mean, that's the end of the diagram. So the next thing I would do is look to see, are there any arrows in this diagram that are not perpendicular or parallel to other arrows? Like, is everything on this diagram along given axes? And the answer is, in this case, yes, which is why I'm going to move on and answer other questions about it, right? But no, if there was some kind of diagonal arrow or something that was off kilter from the other arrows, then the next step I would have to do is divide that arrow into component parts before moving on and make a third diagram. Sometimes, generally, we'll do that, but there's no need for it here. The one last thing I'm going to say is what you could do, what a lot of websites or books or something will do, is you could also note, like these arrows are in the opposite direction. And I also sort of intend, I didn't do it perfectly, but I intend to have these arrows more or less the same length on the page. I'm actually trying to signify that I believe with these little hatch marks I just made, I believe those two arrows should be the same length, i.e., I have reason to believe that those two forces are not only opposite direction, but also equal magnitude. But let me tell you why I believe that. I'll agree. It's all about F net equals ma, right? I believe that F net equals ma. So because of second law, because of Newton's second law, I believe that whatever the weight of the apple is doing, pulling the apple down, I believe that must be in this, it seems to me that that is balanced by whatever the desk is doing, the table is doing in the upward direction. The reason I believe that is because the apple is not accelerating up or down, right? Again, one of these points is like obvious, but it's not. Like the A of the apple is 0, and there's two F's in opposite direction. Therefore, I believe the two F's must be equal in magnitude. Otherwise, the apple, like if they weren't, the apple would be like flying up or crashing through the table. So I believe that so foreshadow or spoiler alert, I do believe those arrows are equal. I'm trying to emphasize right now, just because there are two arrows going in the opposite direction does not always mean they're equal. Arrows are, and just because there's one arrow doesn't mean there's automatically two arrows. We'll see that in a minute. There could be any number of arrows in a diagram, and they might or may not be balancing each other. If there's any acceleration occurring, then they're not balancing each other. There's no acceleration occurring in this situation. Therefore, I think that arrows are balancing each other, but I think that because of Newton's second law, not third. So now let's go on and see why I'm saying that. But let me switch the screen. So we're going to go to number 4. Okay, number 4. Yeah, okay. So now in number 4 on the homework, it says write down the Newton's third law pair implied by each arrow in your FBD, in your free body diagram. So now it's asking me about Newton's third law. Okay, now Newton's third law is the action reaction one. I mean, the way I say, I think the correct way to say Newton's third law is, hold on, I'm just switching back the screens. Sorry. The way to say Newton's third law is if I push you, then you push me in the opposite direction, but with equal magnitude. It's a deep law. Now, part of my argument is it's a deep law, but what it's really capturing, it's just yet another implication of Galileo's principle of relativity. It's just like if the Earth goes past the sun at if the sun is going past the Earth at 65,000 miles an hour, then the Earth is going past the sun at 65,000 miles an hour. It's just like that same idea. If I push you, you're pushing me. If I married my wife, then my wife married me, right? And that's not an accident or like I mean, that's nice, but it had to be that way. Same thing. There's no way I could push against the wall without the wall pushing me, which is why if I push a wall, like I go, flying that way. And the force is equal in both in the magnitude of force is equal in both directions according to Newton's third law. Every force is a symmetric interaction between two objects. It doesn't matter who you think of as the pusher or the pushee. That's like in your head. That's a matter of perspective. It's just a push or a pull, right? So it's asking us now to analyze that in the context of or to apply that to this situation. And what I want to be really careful here, it seems simple. I mean, it is simple, but it's deceptively simple. What I'm trying to say is, well, okay, I'll go one at a time. In that diagram, right? First of all, I have this MG. The MG arrow, the MG arrow means that the Earth is pulling down on the apple, right? That's what the MG arrow means. You could consider that an action if you like. But now look back at your system schema. When we were looking at that interaction as an interaction before we got into arrowheads and all that, notice what the system schema is really trying to get across. If the Earth is pulling down on the apple, if that is like the action, and that's an arbitrary word. Anyway, if that's the action, then the reaction, so to speak, is that the apple is pulling up on the Earth. Now be very, notice this, please. It's really simple once you get it. I don't mean easy, I mean simple once you get it, but it really is different from what a lot of people think or think they think or think I meant when I said Newton's third law. Like I'm saying, that downward arrow in the free body diagram is an action, and the reaction to it is in some other picture that I haven't drawn, or some other free body diagram that we haven't drawn. The reaction to that arrow is that the earth is being pulled up by the arrow, by the apple. They are interacting with each other. They are having a tug of war. That interaction goes both ways. I'm saying, and I will move on, but I'm saying, notice that's all about the mg arrow. It has nothing to do with the normal arrow. Notice I'm saying, and I'm really trying to make a point of saying, yes, the normal arrow and the mg arrow are opposite in direction. And yes, they're even equal in magnitude, but they are not a Newton's third law pair. They're not there because of Newton's third law. They're not what Newton's third law means. That is not what action reaction means. In fact, honestly, that's why I don't like when people say Newton's third law is for every action, there's an equal and opposite reaction. That makes it sound like that's too vague. That makes it sound like when an apple is pulled down by the earth, then automatically it's going to be pushed up by a table. That's not true. Just because the apple is pulled down on earth doesn't mean automatically by law there has to be a table. We put a table there. I mean, I'm not kidding. Apples can, otherwise, if that were a law, then nothing would ever accelerate or fall at all, right? Apples can be pulled down by the earth. And what happens automatically, if they are, is that they're pulling up the earth. And that is happening. Now, and don't forget though, F equals ma. I mean, when an apple falls to the earth, it's pulling up on the earth with 9.8 newtons of, or whatever, with the same number of newtons as it's being pulled. But of course, the earth is like really massive. So in response to that, it would only accelerate a tiny bit. So first of all, even if nothing else were going on, you'd barely notice what's happening to the earth. The force would be the same, but the acceleration would be tiny. But also, statistically speaking, just because if you drop an apple to the earth, I mean, why would you assume that someone isn't like, that your counterpart in China isn't doing the exact same? I mean, there's all kinds of things happening on earth all over the earth. So just because you drop one apple doesn't mean like you're going to like, throw the whole game out of orbit. But you see what I'm saying? And I will move on, I promise. But I'm saying mg is the action, n is not the reaction. The other side of mg is the reaction. That is one pair implied by the diagram that we just drew. The other pair is the normal means. Now, if you wait, should I almost want to stop and ask for responses in the chat here. But no, you probably want to kill me. All right, I won't. But if I take long enough to write this down, you may want to, in your mind, ask yourself, what's the answer to the other one? To the normal. Like the normal, just follow the pattern here. The normal means the table pushes up on the apple. That's the normal force, right? So the reaction to that is that the apple pushes down on the table. And that is true, right? Like, I mean, just picture it. That's happening. So I'm going to move on. I always say that. Every arrow in a free body diagram is an action to a reaction that occurs in some other free body diagram that we haven't drawn or is made explicit in the original system schema. But so the number of forces in the universe has to be an even number, but the number of forces in a free body diagram doesn't have to be an even number. The actions and the reactions are never in the same diagram. That's what I'm trying to get across. If they were, nothing would ever accelerate. Okay, I'm going to move on, but that's the deal with that. All right, so I'm going to, so that's, all right, that's the answer to 4. Okay, luckily now 5 could be a whole other rabbit hole, but I've already rabbit holed it. I mean, number 5, like I've already made an over stink of. Number 5 says, like, compute the force that the entire Earth exerts on the apple through gravity. So, in other words, it's asking you to, what is weight? And we've already established weight is m times g. In other words, in this case, numerically. Right, and it explains like how hard would the Earth have to pull in order to make the apple fall at or 9.8 or 10, you can round to 10, whatever. If the table weren't there, like it all explains the things that I explained yesterday. So the mg in this case, so the apple was how many kilo? It was 0.5 kilo. All right, so yeah, I'm saying 9.8, but you can totally round to 10 and you should on the exam or whatever. You can always, as long as it's not the lab. Um, so the weight equals like 5 newtons. That's the weight of the apple. 0.5 kilograms times 10 meters per second squared equals 5 newtons. That's the answer to 5. Okay, and then 6, I basically already explained also. 6 says, it says use Newton's second law to compute the force that the table exerts on the apple. I mean, so the answer is the normal well, it's saying that it's what I already said in English, but it's saying like this. Well, so actually, let me slow this down for a second. 6, well, it says use Newton's second law to compute what the normal force equals in magnitude. So I already said it in English, but I'm gonna slightly slow it down because this is our first example of doing an actual Newton's law, Newton's second law computation. And the way we do the computations are from the diagrams, from the free body diagram. Okay, so always best to see these examples in a case that's not too overly involved. So what we're saying is, according to the diagram, right? In the diagram, we had an upward force. We had two forces. They were in the same axis. Well, okay, hold. So I'm gonna like what we know is F net equals ma as a vector equation. Always. Then what we know that always means is it's separate equations along separate axes, which is why all of our diagrams always have to have clear axes going on. Well, everything is happening in the y-axis for this diagram, right? Like here, nothing's happening in the x-axis. Everything's happening in the y-axis. So now we look at all the forces acting on our y-axis and we plug them into the left side of F net equals ma, but we plug them in paying attention to direction. Like the normal force is pointing, we'll call the up direction positive and call the down direction negative, for example. So we would have that the normal force is acting in a certain direction and mg is acting in a different direction, so it gets a minus sign. To be really clear, sorry, let me make this really clear. I'm really saying this. You see, I'm adding up all the forces in an axis, all of them. And I'm just copying the terms from my picture. That's why the pictures are so important. And all of that together will equal MA along that axis. That's how this works, right? So, because again, I cannot emphasize enough. I don't know why I'm getting myself all, but like everything in physics until like 1905 is F net equals ma. Like really, the centerpiece of physics is F net equals ma, and the whole issue is what do you plug in for F net? Like for everybody, that's the issue. What goes in the left side of F net? Because it's always some long expanded thing. So the way you know is you go term by term, the arrows that are in your picture, one axis at a time in your free body diagram. And you know that you can trust your free body diagram if it came from a properly drawn system schema. Like, okay. So this would be the F net equals a statement in a comparatively simple scenario like this. And it's asking us here to solve, like often we'd be solving for acceleration. Here, it's asking us to solve for a particular force. How could it ask us to do that? Because we already know that the acceleration is zero. That's the key piece of information. The acceleration is zero. Therefore, one force equals the other force in magnitude. Like I just dragged the mg to the other side, right? And therefore, like in a sense, that's the answer. But since we have numbers here, so here n equals whatever we just figured out mg was before, 5 newtons. Or if you want to round, if you don't want to round and you want to keep it as 9.8, that's fine too. But there's no reason to do that if it's not. So you could say, you know, uh, 49 whatever newtons. But this is the answer I get. I mean, you could get like 4.9 newtons. I mean, but that's the answer. And again, I'm just trying to emphasize, I will move on. I'm just trying to emphasize that is not because of Newton's third law. That is an application of Newton's second law. And any application of Newton's second law from here on in can look more complicated, especially in Lab 5. It can look very complicated, but it is literally this procedure. Okay. So for example, it is this procedure I promise you, in part B of this whole problem. I'm going to leave that. It's the same deal, only it's all the same deal, part B of the problem in the homework. But the acceleration is now 3 rather than 0. So you just do all the same things, but you plug in a 3 instead of 0. So then it gets to the problem for the duck in the elevator. Let me think about this for a second. I mean, let me make a decision of whether I want to do this. Um, uh, I'm going to stop for a second and look in the chat. Wait. Oh, I knew there was something in the chat. All right, awesome. Great question. Great question in the chat a minute ago. Why did I? So the chat said, and please do submit for these points. And again, by the way, again, even though I am behind, all these, anytime you've submitted for points or turned anything in, it's all there. You all know that, right? I mean, it's in the Google Classroom, and it's organized. So it's not going to get lost. Anything you've ever submitted for points, I promise you, you are getting the points, it's, even if I've taken longer to get them to you than I wish I had. So for example, the person that's in the chat right now asking this question, please submit for the points for this question because it's totally helpful. And the question is, why did I cancel out the x-axis? Is it because the apple is just like not moving or what? Yeah, great question. And yes, but even more specifically, it's because we have, because the apple is not accelerating along the x-axis, meaning that in this problem, we were not told about any kind of left or right activity. In fact, I think we were specifically told that the apple was sitting still. I think we somewhere we were yeah, we were told that the apple is sitting on a table. So in fact, the apple is not accelerating along any axis at all. It's very explicit and fair to believe that the A along every single axis was 0. And we use that fact. On the y-axis, we use the fact that the A was 0 to then figure out things about forces that were acting on the y-axis. But then on the x-axis, to answer your question, the x-axis I entirely crossed out because it turns out on the x-axis, there's no acceleration and there aren't even any forces acting. Like literally nothing was happening on the x-axis. So 0 equals 0. And I'm not being sarcastic. Like, because she or he is right. Like, every time you do a Newton's law problem, you absolutely have to focus on each axis. You have to look at each axis. But once you determine, or if you determine that there's literally no forces and no acceleration on a given axis, then we don't have to pay attention to that axis anymore. But it was a spot check. I mean, yes. So I think explicitly my answer is because literally there were no forces even acting on that axis, which I didn't know until I drew my pictures and saw specifically my free body diagram and then saw there's no horizontal arrows. So I'm done with that axis. I hope that, but that's a great question. Um, okay. Yeah, thanks. All right. Awesome. Awesome. So I think what I want to do, I think it's best for all of you, especially since Lab 5, like sort of in all of this, what I'm trying to do is get you in best possible position to do the most with Lab 5. And I'm not going to fit it. Like I'm not going to do everything in 15 minutes. Um, Lab 5 is a big lab. It's like important. It often is on the final exam. And it's hard at first. I'm just warned, like, don't give up. Like it may be intimidating at first. Like, so Lab 5 is all about this. But there's two other issues. There's two other big issues that get involved in Lab 5. Okay. One is the issue of friction, and the other is the issue of angles. So I'm going to try to skip to those issues right now. Okay. Not skip, but like, in other words, the duck in the elevator is a great problem. If I get a chance to talk about it again someday, I will. But I'll tell you the punchline of the whole duck elevator problem, like in the homework, the punchline of that whole problem is it's still a purely vertical one like this. But there you have like a duck, accelerating up and accelerating down because it's in an elevator. And the whole deal there is to understand there's no such thing as an elevator force or something. And there's no such thing as an acceleration force. Like the whole deal there is it's the same free body diagram as we just did here. That's what it's really trying to test your understanding. That if there's a duck on a surface in an elevator and that's it, and then the only forces are the surface pushing up on the duck and the earth pulling down on the duck. That's all that's going on to that duck. But if that surface happens to be the floor of an elevator, okay, that means that surface is pushing the duck up harder than the weight of the duck is pulling down. Like it's the same, everything in the duck problem is the same free body diagram, but and the same Newton's law statements right here that I have in blue. It's going to be N minus mg equals ma. Only in that problem, A doesn't equal 0. So N and mg are not balanced. It's trying to, and that's how elevators work. Like the force that's accelerating the duck up is a normal force that's just bigger than the duck's weight. Or when it's going down, the normal force is smaller. Okay, it's trying to drive home that normal forces don't have to balance gravity at all. And it's trying to drive home that we don't make up forces just because something's in an elevator. We don't like say there's an elevator for or so, like the only thing that is a force is whatever's touching you is what we're trying to. Okay, so that's like the deal with the elevator duct, the big picture. What I want to get into now, um, is so I'm going off the homework now. Okay, I'm gonna try to summarize the two other issues that you need for Lab 5 and for future material. Um, okay, friction. Friction. When two forces, this all goes back, everything I'm about to say now for 11 minutes, it goes back to this weird, seemingly weird technicality that I introduced when we talked about the system schemas on Monday. I said that in Monday, I said if two surfaces push against each other and the surfaces are rough, they're realistic, right? Right. Um, I said that in the system schema, you have to draw two lines. Because I said that when two rough surfaces push against each other, they do this. But then if they're rough, then they sort of grab onto each other. Then, like if you were to look really closely, microscopically at the surfaces, they look like bumps and ridges, or they look like teeth of a comb, and they lock into each other. And so the more you press them against each other, the more they lock into each other, and the harder it is to rub them or slide them alongside each other, right? So the push, so the perpendicular push is always accompanied by a parallel push. The perpendicular, if the surfaces are rough. So the perpendicular push, we've already said, is called the normal force. The parallel push that goes along with this, that comes as an associated effect. Oh, okay, great. Thank you for letting me know, direct chat. But yes, have a great spring break, direct chat person, not anybody else. Um, uh, the force that is parallel to the plane of contact is called friction. Right. And the first thing I want to say is that that's all that friction is. It is a pushing force that occurs between two rough surfaces, but it's the component of the pushing force that is parallel to the plane of contact, as opposed to the normal force that's perpendicular to the plane of contact. They come, you cannot have a friction force without a normal force, like literally. And okay, you can have a normal force without a friction force if the surfaces are not rough. But but if you're going to have a friction force at all, it is just it's just the 90-degree effect of the normal force. So okay, so they're qualitatively linked together. In fact, they're quantitatively linked together, as it turns out. The more normal force, once you have friction at all, the more normal force you have, the more friction force you have. In fact, in a very nice way, I mean, within reason, it's in a very nice way. They're actually linearly dependent on each other. They are directly proportional. If you have a rough surface, the harder you push the surfaces together in newtons, the more friction you will get in newtons. Okay, they're each a force, right? And in fact, it's like it's like a straight line to a point, which is very nice. A straight line with y-intercept 0, i.e., if you don't have any normal force, you're not going to have any friction. It's a straight line with y-intercept 0 and with a slope. I'm just going to blow this up now. With a slope like a rise over run, right? But in this case, rise is friction force and run is normal force. A slope that we call mu. Mu is a dimensionless ratio of newtons per newtons, right? Mu is a number. Mu is a dimensionless ratio of how many newtons of friction arise from each 1 newton of normal force when two rough surfaces push together. Okay, the higher mu is, so mu is like a dimensionless number. It generally ranges from 0 to 1. Like it's a fraction or a decimal. Sorry, the diagonal arrow. The diagonal arrow. Well, it's a graph. This is like a graph. Like the diagonal arrow, is the graph of if you were pushing of friction as a function of normal force. So it's like the diagonal arrow, it's not a vector. I mean, it's a good question. The diagonal arrow is like not a vector. It's just like it's a representation of how much friction force you get per each newton of normal force. So it's saying that if you have two surfaces, okay, great. Thank you for the, okay. So, right. So to everybody, I'm saying if surfaces are rough, The harder you press them together, the harder they are to rub across each other. So the more normal force you give them, the more friction force you'll have. The slope of that relationship is called mu. It's so the higher this number mu is, that means the more friction you're getting per each unit of normal force. So what mu is, and now why would that be? Like, why would in some cases, why in some surfaces would you get a lot of friction for a given normal force, and in others you press down the same amount, you get like a lot more friction? Why would the graph of some be steeper than there? Because some surfaces are rougher than others. So mu is a dimensionless number that literally is just the measurement of how rough a surface is. Mu is called, sorry, mu is called the coefficient of friction. It's a roughness rating. Like if mu is like 0.1, it means the surfaces are like glass or something. If if it's like 0.0005, it means like it's a cushion of air, like an air hockey table. But if mu is like 0.5, maybe it's like ceramic or something like that. And then if it's like 0.9, it's like rubber on rubber. Do you see what I'm saying? It's just literally a number that says how rough two surfaces are. And so literally, if you want to turn this into an equation, which everybody does, I'm literally saying at the end of the day, to figure out the friction that one surface exerts on another, the friction force would be the mu, the roughness, which is usually given, times the normal force that one surface exerts on the other. Friction is fun. Physics is fun, right? But no, seriously, that's a real equation. F, as in force of friction, equals mu times the normal. Note again, F is the force of friction. N is the normal force. We're saying that if you figure out the normal force from a free body diagram, and that's how you do. Like the normal force, you don't memorize. I mean, write this down. Here's the deal. I'm literally putting down the cannoli. I'm not going to write anymore. It's 12:02. I might even be done like a minute early for a change. If you just write this down or follow this, and we'll be done. I'm saying, now I forgot what I was saying. I'm saying there's no formula for the normal force. People always think there is, or they want what there isn't. The normal in any given situation, what we were trying to just see in the last Apple problem we did, the normal force is something you figure out from F net equals MA. The normal force will be on a given axis in your FBD, and then you do F net equals MA along that axis, and you'll figure out what the normal force is. It varies from situation to situation, but you figure out what the normal force is from your diagrams and F net equals MA. Then you multiply that by this pure number like 0.1 or 0.4 or 0.7, and that will give you a new number measured in newtons. That new number is how much friction there is along a different axis. That's how this works. The harder two things are pressing this way, the harder they will rub or resist each other that way. Friction, roughness of materials, what ties together the interaction along two perpendicular axes. So the number mu is not a force. It's just a number. It's a coefficient. You use it, you multiply the normal force by it, and you get the friction force. And that's like important in lab 5. There's more to say about that, but it's 12:04. Have a very lovely break. Have a very lovely break and try to break and let things break around you. And if there's any quick questions, I'm here. I'm turning off the recording, but other than that, have a great break. And obviously, you can reach me by email. Blah, 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 blah. Yes, have a good break. Hopefully, you have mine. You can reach me. Okay. Yes, have a good break. Okay.